In this video today I will show a space shooting game environment and use it to train a deep reinforcement learning agent. Let me first briefly introduce the design of this game. Players need to control the spacecraft to shooting meteorites. Players will get points from smashing it. Being hit by it will deduct health points. When losing health points, they will get a certain invulnerable time. After the player loses all health points, the game will end, and the generation of meteorites is random, with different angles and speeds. One difference is that when doing training, the agent's goal is get a total of 200 points. And let's say this is the main code of our game environment. And we set the action space here with total of 18 action spaces. And then it's a resource class. It's made here to facilitate the management of resource rendering. And this is the game class that initializes the game interface and the parameters that need to be recorded in the game. And more importantly, it resets the player. And meteorites and score functions, which are used in every update. So this function is very important. And this is a processing function based on the player's position movement, survival time, and final goal, which all affect the player's score. And this function checks the collisions between the player and the meteorites and updates the score by shooting at the meteorites. And this function that handles some rendering. And this function is a function that handles some display some basic information and some game states in the game interface. And this will display some parameters related to reinforcement learning displayed in the interface. And then this is the player class, which defines the player's attributes such as the shooting cooldown and the invulnerability cooldown and the initial health value. A get state function is used to obtain the state, and our state space is defined here. After many improvements, I upgrade the state space to 90 dimensions, which now include the player's XY position and XY speed, and lives, and so on. Then it also records the information of the lasers and 10 meteorites that have been fired. Here, only meteorites whose y-axis is larger than player's y-axis will be recorded, because I think meteorites above the player's position and have a greater threat to the player. And take action function define some possible operations corresponding to the action space. Next are some functions that update values. And this function is for processing human player operations. Then some environment-related classes are defined here, just like star, laser, meteorites, and handle animated explosion. Okay, and then some variables are set here, as well as reward setting. It's very important, and I change this number many times. And the next function is called when human player control. Therefore, running the main function directly will enter the human player control mode. And we can try it. As you can see, I can control the spacecraft and press the space to shoot. And you can see the score and position and the cumulative reward and survival time. Okay. Okay, after this, let's take a look at the implementation of deep reinforcement learning agents. Deep reinforcement learning is a reinforcement learning algorithm that uses neural networks to approximate Q-value functions. And we define a multi-layer perception NLP with an input layer, a hidden layer, and output layer. The activation function uses ReLU. And in this part of the code, the deep reinforcement learning agent is defined. And here are some training-related parameters. And here are the dimensions of state space and action space, and the size of the experience replay buffer, which is used to store past experience, and the discount of the discount value of future rewards, and the initial absence rate and the minimal absence, also called exploration rate, which ensures that the agent always has a certain probability of choosing an action, and the exploration rate decay coefficient, which is multiplied by this value after each update, and the number of training rounds learning rate, the frequency of target network updates, and the size of the scaling network updates, scaling the reward. And we set up the main network, the target network, and the optimizer. And the remember function restores the experience in the experience replay buffer, and the act function selects action based on the current state, and selects action based on action, which may be a random action or the action with the largest Q value. And in the replay function, we will sample a batch of experience from the buffer for training, calculate the current Q value and the target Q value to update the parameters of the main network, and update the target network regularly. And in the update target mode function, copy the weight of the main network to the target network. And next is some some true functions. And in this project, we will use experience replay, target network, and absent greedy strategy. And the experience replay buffer stores the agent's past experience and readily samples from it during training. This helps break the correlation between experience and improve the stability and efficiency of training. And the target network is used to calculate the target Q value and regularly update the weights of the main network. This can reduce instability during training. And during training, the absent greedy strategy is used to balance between exploring new actions and using the best known actions. And let's take a look at the training file. When executing its file, two parameters are set. One is whether to render, and the other is a number of training rounds, which can be selected when entering the command line. And then the code for join training data is followed, including the cumulative reward training loss and absent value changes as the training processes. And next, the training agent function is the core function for training, which is responsible for initializing the environment and agent, prefilling the experience replay buffer and training. And this is the prefilling code. And this is the training code. And this will show some parameters in the training process. Because we have done many training before, we did not get the expected result, and we have made many adjustments to the parameters, state space and action space. Therefore, the rendering method was chosen in this training, so that the behavior of the agent This interface is the training interface. We can see that the agent seems to have a certain behavior of avoiding meteorites. But we can see from the images generated by the training, most of the current rewards are kept in the same range, and the origin line is the first figure represented in the average of 100 rounds. And some rounds reach 100 or even 200, which is the target score, but overall there is no steady upward trend, which means that the agent has not retained the high reward strategy to achieve the goal. According to the second figure, the loss is reduced to about 0.08 not long after the training, and there is no large-scale fluctuation afterwards, which shows that the network has basically determined that there are no excessive changes. This may also indicate that there may be some problems with the reward setting of the environment, and the model converged to a safe range, which means that it predicts that all action will produce similar mediocre returns, so it will not continue to update. And this is also a difficulty encountered throughout the process, and it also needs to be adjusted step by step to solve its problem. At present, it seems that reward shaping is not smooth enough and the punishment is too large. and the agent cannot receive enough consistent experience to determine and maintain the best strategy. The few times when the goal is actually achieved are random events, so the strategy cannot be strengthened. And then I will continue to shape the rewards to make the reward curve smoother. And it is also possible that some parameters of the game design need to be adjusted, such as the game difficulty is too high and the number of meteorites is too large and the speed is too fast. And therefore, in order to verify the effectiveness of deep reinforcement learning and optimization method, I did a test in the lunar land environment. In this test, I also used experience, replay, and target network technology to optimize the effect of deep reinforcement learning. We can see that the ideal effect has been achieved in this training. From the figure, we can see that this reward is regularly increased and stabilizing at a relatively high position, and the change in loss value also corresponds to the change in reward, which means that the network is changing and approaching the perfect strategy. Therefore, in the future work, in order to achieve the expected effect, I will also shape the game reward and further adjust the parameters. In this project, I learned a lot of knowledge and skills related to reinforcement learning, and also strengthened my ability. If anyone knows how to solve this problem, I hope you can give me some suggestions. Thank you very much. Thank you for watching.